Okay, so we have talked about this optical amplifier thing inside this optical resonator for lasers. What an optical amplifier does is that you can think this is as a black box, that you have an input of light and an output of light. So what an amplifier does, in fact, that it increases the amplitude of the input light. It goes from this, as you see over here. Let me grab a board marker. Okay. So this is from maximum to minimum. This is just the amplitude. We call this amplitude. This is A0, let's say, the amplitude of the input light, and then this is the amplitude of the output light. Okay. So if A is larger than A0, this box is working as an amplifier. Okay. So in details, we will discuss also what this amplifier does. But let me first introduce what an observer is. Optical observer. Okay. So it does just the reverse of what the optical amplifier does. And if this is the amplitude of the input light or signal, whatever you call, and this is the output signal, amplitude of the output signal. So you see the output signal is smaller than, so A is smaller than A0. In that case, what we call this system is an optical observer. If just decreases the amplitude of an optical signal, that thing is called an optical observer. So we have to know these, what the absorption and then amplification means. So that's why I just first started with these definitions. So what happens, in fact, in the atomic picture, in the microscopic view? In the microscopic view, this picture represents, okay, these lines are representing the energy levels of an atom or a molecule, okay? You know from quantum mechanics, we know from quantum mechanics that atoms and molecules have not the continuous energy levels, but rather they have discrete energy levels like this, okay? And in the electrons, what does that mean is that electrons can occupy one of these energy levels, but none in between, okay? And by the way, this vertical axis just represents the energy, okay? So that means this first energy level is smaller than the, in terms of energy, second energy. Usually we call first one as the ground state, okay? Ground state energy, the minimum energy level. But usually, I mean, not usually, in fact, this ground state energy level is not zero energy. It has some energy, non-zero energy value. But anyway, it's the smallest value, so we call it in the ground state. So in the microscopic view, in fact, optical observer is nothing but some collection of atoms or molecules which have some discrete energy levels. So what comes into the picture is that these represents the photons, because we are dealing with the microscopic picture, and the microscopic picture sees the light as photons, right? So these are representing the photons, coming photons. Well, what happens to one of these photons in this picture is that one of them is just disappears, but also we have the atom which is in the ground state. The energy level of the electron in the atom is in the ground state, so it jumps into the next energy level. So electrons jumps into the next energy level, and one of the photons disappear. This is the picture of absorption in the microscopic domain, okay? So, what happens? The energy of the photon is absorbed by the electron, and the electron, since it has extra energy, so it can move to higher energies. If its extra energy is just enough to cover this energy gap, then it jumps into the second energy level. So that means one of the coming photons have just this energy difference. Let's call this energy like E2, and this is E1. Sorry. and coming photons have energies like h times frequency. You know, in one single photon, if the photon belongs to frequency f in the electromagnetic spectrum, and its single photon's energy is just hf, sorry. So obviously E2 has E2 minus E1 is non-zero, and it's a positive number. So if this difference in the energy is just enough for the photon h frequency hf, then this happens, okay? This electrons just absorbs one of the photons, and that photon just disappears. Well, disappearance of a photon is not a big deal because the photons has no mass. It's just a pack of energy, and that energy can be easily transferred to electrons. And then that extra energy just raises the energy state of the electron to the next one. Well, of course, if this holds, okay, if HF is less than this difference, then this does not happen. And absorption has some conditions that if the photons are absorbed, then they must have some certain energies, okay? All right. So what do we have in this picture? Well, what you see is that these, atoms in this energy levels and the coming photons, and one of the photons is absorbed. So how do we see this absorption in the spectrum? In the spectrum, that the vertical axis represents the intensity of the incoming light, and the horizontal axis represents the frequency. That means you can change the frequency of the incoming light from any value, okay, to any value. But when just HF, or the frequency, happens to be this equal to this difference in the energy difference between the levels, then you see a dip. You observe a dip in the spectrum, okay? You observe a dip in the spectrum, telling that there is some absorption of the intensity in the incoming photons. So, but the thing is, this dip, or this decrease in the intensity, means that the incoming energy is absorbed, but it does not go to like zero, and also it doesn't have a very narrow width. It's not a single line. That means like frequencies which are other than this difference, so let's say this frequency, just this one or this one, may also be absorbed. And you might think why this is the case. Why this is the case? Because there is always some uncertainty in the energy levels, okay? In quantum mechanics, this energy level is not just a single sharp value. Rather, it has some fluctuations, okay? Because of these quantum fluctuations, we call these quantum fluctuations quantum energy fluctuations. Some of the energies of the photons which are not just equal to but closer to the difference may also be absorbed. So this produces some kind of bandwidth in the absorption spectrum. This is called the absorption spectrum, because we have the spectrum of frequencies over here, and this is the spectrum of incoming light. Supposing that all frequencies are having the same intensity of light, but if you also have this medium that contains this specific type of atoms which have these energy levels, in the spectrum you will observe that this dip right at the frequency or close to the frequencies of this difference in the energy level gets smaller in the intensity. Why? Because some of the photons are absorbed. Why don't we have this dip goes to zero? Because probably there is not enough atoms that absorbs all of the photons. That's might be one reason. So, but of course, this dip can go up to zero. Well, usually you don't observe zero intensity because there is not going to be enough atoms in the medium that absorbs all of the photons. Well, at least some of the photons will just fly away without the absorption. So what you see on the bottom page is that you see the medium as quantum mechanically microscopic, but the photons as classical waves. So the classical waves are represented by the amplitudes of the signals. So if the amplitude of the signal is just decreased, then what happens that certainly some amount of the amplitude is absorbed by the electron, and the electron goes to higher energy level. By the way, if you have any questions, you can interrupt me and ask anyway, okay? So, what next? What you see over here, in the first picture, we call that the absorption, the stimulated absorption, if the frequency of the incoming light is just equal to the difference between these energy levels of the atoms. You see there is some incoming light, some amplitude coming, and there are many atoms. These number of different spheres over here represents the electrons belonging to different atoms. So you have, for example, on this picture, 1, 2, 3, 4, 6 atoms over here. But the only 2 of them is just absorbs the some of the energy of the incoming light. So what happens next is that, does these electrons live in the higher energy level forever? Of course not. Okay. So, I mean, this is the case. This happens all the time. Once the electrons absorbs the energy, they jump to higher energy level, but they don't live in that energy level forever. In fact, they live quite a small amount of time. So usually this is in the order of nanoseconds. So they just stay there for nanoseconds, but then they just drop back to previous energy level. Okay. What happens when they just drop back to the ground state? So what happens is that energy is lost now. Okay. So take this electron, goes to this ground state and losing energy. But what happens to this loss of energy? They turn out to be photons. They just emitted to be photons in some spontaneous direction. Okay, so this process is called spontaneous emission. Okay, once the electrons are in the on the upper energy level, and they spontaneously fall back to the ground state, while falling down, they just emit. Every single electron emit single photons. This emission is called spontaneous emission. And you might ask, what is the direction of the photon that is emitted? Well, it can be in any direction. Any direction is possible for the emission. But later we will see that there is a special kind of emission which we call stimulated emission. In stimulated emission, this direction is preferred. There is a preferred direction. And we will see that what this preferred direction is. Okay, so what we see, in fact, in experiments, that we have some variable frequency generated light, and this goes to the vapor cell. In the vapor cell, there are some atoms, there are some mediums that can absorb these photons, and we have a detector over here. While you just span these different frequencies, you just observe at some certain frequency there are some photons coming out. That means there is this spontaneous emission is taking place, and some of the photons right at the frequency of the matching frequency of the atoms inside, they absorb light, and then they just fall back onto the ground state again by emitting these spontaneous photons. And in the spectrum, this is the picture. Well, we have seen this before. And in the real life, what you see, in fact, there are going to be photons coming out in every direction. Okay, and of course the detector over here is going to just measure some intensity which is less than the intensity of the incoming light, if of course that frequency of the photons just matches to the energy level difference. Okay, so what you see next is this picture. Again, we have when an incoming photon, supposing that the incoming photon has just the right frequency that matches the energy difference between these single atoms energy levels, E2 minus E1. But the thing is that the atom is in fact initially in the not ground state but in the excited state. Okay, so the electron of that atom is in the excited state and there is an incoming photon. So what is going to be happen in that case? What happens to the incoming photon? Well, obviously, if there is no any other higher energy levels, well, if in fact there is, but in this picture there is no way that this electron can absorb and go to some higher energy level. Rather, what it does is that whenever that electron sees an incoming photon that just matches the energy difference between its excited level and the ground state level, this electron is going to be forced to go down immediately it sees that coming photon. Even if it were waited for longer time over here, whenever it sees this photon coming, it will immediately, whenever it sees it, it will immediately forced to go back, pushed down to the ground state energy level. Of course, when it does, because of the loss of its energy, it will give an extra photon to the medium. That photon is going to be having just the same frequency of the incoming photon with that of incoming photon, and also it will have the same phase. This is very important. This point is very important. So the picture produces an extra photon, but the extra photon is not spontaneously emitted in any direction. Rather, it goes with the direction with the incoming photon. Exactly, it goes with the same direction with the incoming photon, and in addition to that, it will have the same phase. I mean, the order of its oscillations is just following the order of oscillations of the incoming photon. And peaks are overlapped, the dips are overlapping, so they are in equal phase. This process is called the process of stimulated emission. Because there is an emission, there is an extra photon, but this emission is not spontaneous and the extra emitted photon is not going in any direction, random direction. Rather, it goes with the same direction with that of incoming photon. Okay, this is the important part. In fact, these are the type of emissions that the laser is producing photons, and these produced photons are the photons that are produced by the process of stimulated emission, not the spontaneous emission, but almost all of the photons in a laser light are produced by the process of stimulated. Let me write it down over here. Stimulated emission. So the type of emission that is spontaneous emission is the type of emission that we don't want in laser. Spontaneous emission is not going to work to operate a laser. Rather, we use the stimulated emission. Okay, so you have to know, you have to make a difference between these two types of emission. So next, well, obviously, what happens in a spectrometer if you have some medium that they are initially excited to higher energy levels, and if you have some incoming photons in the medium, then the medium will produce some extra photons, but these extra photons will all have the same direction with the incoming photons. And what you see in the spectrometer is going to be not deep, of course, because initially the intensity of light is, let's say, in this level. But then since after the process we have larger photons, larger intensity, the intensity will increase to some maximum value. Of course, this again will have some bandwidth. Okay, this bandwidth means that if there are some incoming photons which are not exactly the same energy difference but rather close to the energy difference, because there are fluctuations, there is this uncertainty in the energy level, these photons are also absorbed. That's why we have this bandwidth. Okay, it's also important to know why do we have such a bandwidth. That's because of the fluctuations of the energy levels. And this picture shows just the classical picture. If you have a signal which is let's say weak incoming signal, but rather if you have an excited medium, and that medium will act like an amplifier, and it will produce a larger amplitude of output light, so you have a larger intensity. I mean, over here, well, in the intensity is increased by the process of stimulated emission, not the spontaneous emission, okay? And this is an important remark you have to know. This process is the spontaneous emission, sorry, stimulated emission. So, okay, so this picture just shows you the difference between the stimulated emission and the spontaneous emission. So what you see on the left is there are very high number of atoms which are at excited levels. So there's also this incoming light. So when these electrons just sees this incoming energy of the incoming light, which just matches the difference of the energy, they just forced to go down to the ground state by just you know, contributing the higher signal to the output, and the direction is just the direction of the incoming photon, and this is process is called stimulated emission. But if you had some electrons which are at the excited level, there are no any photons in the medium, and then what happens is that these electrons again will drop to the ground state level spontaneously, but this time they will emit these photons in any random direction, not in a certain direction, just like in the case of stimulated emission, but they will emit the photons in a random direction and also in random phases. Okay, so this picture also explains the difference between the stimulated emission and the spontaneous emission. In the spontaneous emission, the emission of photons might happen in any direction without any matching phase, but in the stimulated emission, the direction of the produced light is always the same with that of incoming light. There is always incoming light in the stimulated emission, but in the spontaneous emission, there is no incoming light. There is no light in the medium previously. So they're just, the photons are just produced spontaneously. That's why we call it spontaneous emission. So what this picture tells you. Next picture, this is what you see is some of the atoms, there are some of the atoms, 3 of the atoms are in the excited level, but some of the atoms are, like 6 of the atoms are on the ground state. So there are more number of atoms which are on the ground state than the excited state. If there is some incoming light, that means that incoming light will be absorbed by the medium because there are more number of atoms which are in the ground state. And what does these ground state atoms is that they will absorb the incoming light. Since their numbers are higher than the number of excited level, but what does the excited level is that whenever they see this incoming energy, they just go back, drop to down. But now in this case, in this situation, the system acts like these are not going to go down, rather this energy is going to be absorbed by the ground state atoms because there are higher number of atoms on the ground state. So the net situation over here is that the net absorption. Okay, every time you do this experiment, you will always observe that the incoming intensity drops because of this fact that there are higher number of atoms on the ground state than in compared to the excited level. So what these n's refer to, n1 refer to the number of atoms in the ground state and n2 number of atoms in the excited state. So if n1 is larger than n2, this causes absorption, and there is net absorption in that first case. But if you think about the second case, that there are more number of atoms on the excited state in compared to the number of atoms in the ground state, so what happens is that it just happens the reverse. When you send just some incoming light, okay, or photons, just matches the energy difference between the levels, what the system does is that it will produce a stimulated emission because there are more number of, well, of course, this has the probability that the light will be absorbed by the ground state atoms, but the number of atoms in the ground state is less than the number of atoms in the excited level. So the probability that the emission takes place, the stimulated emission takes place, is larger than probability of absorption. So in that case, what we have is net gain because N2 is larger than N1, and this process is called the population inversion. Population inversion means that if N2 is larger than N1, you have a population inversion. Population means that, some number at some state. This is the population of the ground state. This is the population of the excited state. When the population of the excited state is larger than the population of the ground state, we call this situation as population inversion. So the process over here is net gain, there is amplification, and also the output light is just as having the same direction with that of incoming light with the same phase. This is stimulated emission, and there is no such a case in here. So this is the process that produces the laser. Okay, this is the situation, this is the state of the gain atoms that you need to have. You need to have N2 larger than N1 so that you can produce stimulated emission, and so you can start your laser. This is one of the conditions of laser light, that you must have N2 must be larger than N1. This state is called the population inversion. Okay. All right. So let's now think about a two-level system. Okay. A two-level system has, by the name suggests, that only has two energy levels, 1 and 2. 1 is the ground state and 2 is the excited state. And the question is, if you have a two-level system, can you reach population inversion? Okay. So what you see in this first picture is that there is this pump. Okay. So what does the pump mean? Pump is a process which just takes the energies of the ground state, the electrons, into the excited state. We are just pumping the second energy, excited energy level, by bringing the ground state electrons to this level. Okay, this is the process of pump. Well, the pump might be some extra energy that is given to the gain. This might be electrical energy, it might be maybe thermal energy, whatever, or chemical energy. Some kind of energy just takes the ground state electrons into excited level. So if you continue this pumping the electrons from the ground state to the excited level, you will reach a state in which that there are equal number of ground state electrons and the excited level of electrons. Okay. Well, from this point on, even if you increase your pump process, you will observe that this equality of electrons, which are equal number of electrons in the ground state and the excited level, will not break. It will stay like this. They will have this equal amount, N1 is equal to N2, but N2 is not going to get larger and larger. There is no such case if you have two-level system. Why? Because when you pump, you just this pump might be just, let's say, sorry, we have 10 minutes. This pump might be also an optical pump. Optical pump, what that optical pump does is that you send some photons, you just to bring the ground state electrons into excited level. But the thing is, this optical pump, also what this optical pump does is, whenever they see some number of atoms in the upper level, they force these electrons drop to the ground state level. Well, this process of dropping electrons to the ground state, with the process that electrons in the ground state going up, jumping to the excited level, is going to be same amount of processes, that they are fighting back and forth. But the thing is, since these numbers are equal to each other, there is always being an equal probability of being one of the excited electrons going down or one of the ground state electrons going up. So these probability of going these two processes, stimulated emission or absorption, will have equal probabilities, when these equal probabilities will not make any difference between the numbers in the ground state and energy levels. So what I mean is that N1 will always be N2, and it's not, N2 is not going to get larger even if you increase this pump larger and larger. There is no such case. Once you reach this equality, starting from this, once you reach the equal populations in both energy levels, even if you increase the pumping, N2 is not going to get larger. Forget about it. This is the case. And why is the case? Because I told you that whenever they reach equal numbers of populations in both energy levels, the processes that the electrons go down or electrons go up will have equal probabilities. So this equality, this balance will not break up, never, even if you increase the pumping. So what that means is that with the only two levels of energy, two energy levels, you cannot produce a laser. Suppose you are given a gain medium, some number of atoms that you want to produce this stimulated emission, but you are provided this gain medium only having two energy levels. Forget about it. It's not going to work. So you must at least have three energy levels. Okay? Two energy level is not enough to create population inversion. Population inversion, you know, N2 is larger than 1. The case is that the N2 is larger than 1, but you never get there for two-level system. So what you need is a three-level system at least. You must be provided molecules or atoms so that these atoms or molecules have at least three distinct energy levels. Two is not enough. Well, if you have three distinct energy levels, that means it goes like E1, E2, E3. So initially you start with the ground state. Usually all atoms tend to be in the ground state. You start with the ground state and you have adjusting this to pump mechanism so that the ground state electrons are just jumping to just the third energy level. If you pump them with this energy difference E3 minus E1, these electrons will not go to 2, but rather they will go to 3, because the energy just matches, the pumping energy just matches the difference between energies E3 minus E1. So, well, what happens is next is that, so whenever the electrons get there, the highest energy level, which is E3, they will drop to this E2, not directly E1. Somehow, the process of dropping of electrons just from 3 to 1 is forbidden. And this is the forbidden transition. It's called in quantum mechanics forbidden transitions. Some of the transitions are probable, some of them is forbidden, and I'm not going to tell you why this forbidden transitions, because it requires some understanding of quantum mechanics. But you just take it as a rule, okay? Just take it as a rule. If the electron is at a higher energy level and there is a choice of going from there to this one or this one, if there is this choice, more than one choice, some of the choices will be forbidden. So in this case, going from 3 to 1 is forbidden. It is only allowed going from 3 to 2 and then 2 to 1. 3 to 2 and 2 to 1 is allowed, but 3 to 1 is forbidden. So this is, kind of rule, and it takes some quantum mechanics to explain it, but you take it as a rule. So what happens then over here? Once you populate the third energy level, the laser transition levels are from E3 to E2. Whenever you get these levels starting populated by the pump mechanism, even from the first electron that starts pumped by this pump and then goes to third energy level, even at the first step you reach population inversion, because there is no any electrons initially in the second energy state, and N2 is 0. Whenever you get at least one electron in the third energy level, you get population inversion. So N3 is larger than N2. So right away, starting with the first electron, you just reach population inversion and you're ready to go for laser operation. I hope you understand this. 3 energy level is required for population inversion, and the population inversion is must required for a laser to laze, to start producing laser photons. Okay, and just keep this in mind, that there is only one way to reach population inversion. At least you must have 3. 4 also is okay. Larger than 2 levels is okay. Every system that larger than 2 energy levels work for lasers. Usually in real life, in applications, most of the lasers are 4 energy levels. There are also 3 energy level lasers, but most of them are 4 energy levels. You have an extra 4th energy level. Usually in between the 4, 3, 2, 1, in between these 2 energy levels, this is lasing occurs from 3 to 2, and then the other levels are just the transition levels. Okay, so next picture is sorry. Again, you have this 3 energy level system, and you're just having a pumping mechanism that takes electrons from ground state to the 3rd energy level. And somehow, if you have just initially some photons that goes in this direction, that just matches this energy difference E3 minus E2, then your medium will produce stimulated emission photons, and these stimulated emission photons will be photons of laser. Okay, so in this picture is not just a pictorial representation of the lab. You have this amplifier region, and this is the medium, this is the optical oscillator, and there are mirrors over here, and there is this also pumping mechanism. The pumping mechanism pumps, if pumping might be optical. If the pumping is optical, this laser is pumped by another laser, and then this pump photons are just making these transitions from here to here. Okay, and next is that after this transition, these photons at the 3rd energy level drops to 2nd energy level by using this stimulated emission process. And this is the spectrum that you see. This is the bandwidth of lasing. Okay. All right. So for this week, I will stop here. Okay. And next week, I will go with how a laser starts. And for this week, that's enough. And I will see you next week. If you have any questions.